All right, so this is chapter 4, and in this chapter, we are going to be looking at exponential and logarithmic functions. In this first section, we are going to be looking at the graphs of exponential functions and getting a little bit of experience with how they work. So exponential functions look like these examples here, where we have a number in our base, and now our x is in the exponent. There are some restrictions on what the base can be. The base cannot equal 1, and it must be positive. So we might see variations of this. We might have some different shifts and things like that. But that's what exponential functions look like. And we have some examples down here of things that are and are not exponential functions. There is a typo here real quick, so I do need to fix this one here to be 2 to the power of x. And all of these are examples of exponential functions. I have 2 as my base and x in the exponent. Here I have 10 and then negative x in the exponent. Your exponent can be negative. 3 and then x plus 1, so we can have some shifts here. And I can have a base that is a fraction or a decimal, 1/2, as long as it's positive. And then x minus 1 is my exponent. These are not exponential functions. So a base of -1 can't be negative. A base where we have an x to the x power that's not exponential. My base being 1, again, not exponential. And then x squared, that's actually a polynomial, which we've been working with most of the semester. So anytime we have learned a new graph, the way we initially explore what the new graph looks like is we typically make a table of points, and that's exactly what we're going to do here. So I am going to graph y equals 2 to the power of x, so x and y. And we're going to use the points -3, -2, -1, 0, 1, 2, and 3. And plugging in -3, 2 to the -3 power. Well, if you think of those exponent rules we learned at the beginning of the semester, if I have 2 to the power of -3, that moves into the bottom, 2 to the power of 3. And 2 cubed is 8, so this would be 1/8. Okay. Similarly, 2 to the -2 power equals 1/4. 2 to the -1 would be 1/2. Anything to the 0 power, hopefully you remember that exponent rule as well. If I have any number to the 0 power, that's equal to 1. And then 2 to the first power is just 2. 2 squared is 4, and 2 cubed is 8. So we have some points to work with here. And I'm going to go ahead and plot those points. So I have -3, and that's 1/8. Really small decimal there. -2, and that's 1/4. Still very small decimal. Plugging in -1, we get 1/2. 0, we get 1. Plugging in 1, we get 2. Plugging in 2, we get 4. Plugging in 3, we get 8. And this is the shape of our graph. So this is an exponential function, and this is a growth, because as we move from left to right, my function is getting bigger. Now, similar to the rational functions that we saw in the previous chapter, as my x values, if I plug in bigger and bigger negative values, so -100, -1,000, -1,000,000, I'm going to get really, really, really tiny decimals, but it's never going to actually equal 0. It's never going to touch the x-axis. And so what I have here is a horizontal asymptote of y equals 0. All right. Let's do the other problem here. We have f of x is equal to 1/2 to the power of x. And again, I'm going to make a table of points. And I'm going to use the same x values, -3, -1, 2, -1, 0, 1, 2, and 3. And if I plug in -3, let's kind of review briefly what that looks like. Having 1/2 to the -3 power. Well, that's 1 to the -3 power, and that's 2 to the -3 power. Well, negative or 1 to the, actually, let's think about it this way. Remember that negative exponents move. So this is going to bring the 2 up top and be a positive exponent, and the 1 on bottom and become a positive exponent. 2 cubed is 8, and 1 cubed is 1, so this is equal to 8. Similarly, -2, if I have 1/2 to the -2 power, that will be 4. -1, 1/2 to the -1 power will be 2. Anything to the 0 power is 1. 1/2 to the first power is just 1/2. 1/2 squared is 1/4, and 1/2 cubed is 1/8. So we have all those points. Just like the previous example, we can go ahead and plot them. And at -3, we had 8. And at -2, we had 4. -1, we had 2. 0, we had 1. And then a 1 was 1/2, 1/4, and 1/8. I'm getting smaller. So this is an exponential decay function, because as we move from left to right, it is getting smaller. And just like we saw with the previous example, we have this horizontal asymptote here that my function is getting closer and closer and closer to, but never actually equaling. So that is y equals 0, that horizontal asymptote. And those are two very basic exponential functions and their graphs. So these are the shapes you could expect to see. Growth functions generally have this shape here. Decay functions generally have this shape here, but we can do the same kind of shifting and shrinking and all of that that we have done with other examples where we add values on the end and shift it up or down or left and right. There are some special examples, one of them being the natural exponential function, which you will see a lot in calculus. The number e is the number about 2.7, and that is called the natural number. So this is the natural exponential function. If your b value is greater than 1, if your base is greater than 1, then it is a growth function. If your b value is between 0 and 1, then it is a decay function. And then these rules here are just the rules that we used to evaluate those up above. If I have b to some exponent up top, I can move it up top and make it negative. I can pull out that negative. Those are the exponential rules we went over at the beginning of the semester that you can use again in this section. So this next example here asks us to determine if the following functions are growths or decays. So here I have 3/2. 3/2 is 1.5, and that's bigger than 1. So this is a growth function. 4/5, if you type 4 divided by 5 in your calculator, you'll see a decimal smaller than 1. So this is a decay. Now these next two are a little bit tricky because they have a negative in the exponent. So if you have that negative in the exponent, it's kind of like it's the opposite of what you would think. This 2 to the negative x is the same thing as 2 to the -1 to the power of x. Like I've separated those exponents there. And now I just have an x here. Well, 2 to the -1 is the same thing as 1/2 to the power of x. And now we can see that that function is a decay. Similarly, here I have 1/3, and I can put that to the -1 power and then to the power of x. Well, 1/3 to the -1 would be 3/1, or 3. And 3 to the power of x is a growth function. Okay. All right. So move on to the next example here. And here we can see that we have 2 to the power of x, and then g of x is 7 to the power of x, h of x is 1/2 to the power of x, and then j of x is 3/4. And we want to match these functions with the four graphs we see here. I'm going to put these in different colors to more easily distinguish them here. And then we will go ahead and match them up. And I haven't been super careful drawing over them, but hopefully you'll be able to distinguish between the two, or between the four rather. So let's first distinguish between growth and decay. These two functions here are growth functions. They have a base greater than 1, and these are both decays. So these are the decay graphs. So blue and green are over here, and pink and orange are over here, and we need to figure out which one matches with which. Now, the larger your base, the steeper your graph. So 2 is smaller than 7. 2 is going to be a flatter graph than 7 to the power of x. And so I know that this orange function here is g of x. That is the steeper function. And then 2 of x to the power of x, f of x, is this flatter. Oh, you know what? I switched these around. I'm sorry. These are the decay functions. The steeper function is this green function here. Sorry, this is g of x. As we move left to right, it's getting bigger. So this is g of x, and then this is f of x. These pink and orange are the decay functions. So these are decaying. These bases are obviously less than 1, and these functions, as we move left to right, are getting smaller. And so the closer these values are to 1, the flatter it's going to be. So almost like the smaller your fraction, the steeper your graph. The closer this value is to 1, the flatter your graph will be. So 3/4 is closer to 1 than 1/2. So that means that j of x is this pink function here. That's the flatter function. And then the orange function here is 1/2. That's h of x. That's our steeper decay function. Let me try to make that look a little clearer here. So, like I mentioned previously, we can shift these graphs up, down, left, and right. And I didn't break down all of these separately because we've done so many graphs now where we have these shifts. And so this is kind of a summary of all the shifts that we have so far. And we're applying them now to the exponential function. And you know what? I think it might be, well, we'll try and make this all one video. I was going to try and break it up here, but I think we can get it all in one video. So this plus c on the end minus c shifts this graph up. This shifts it down. Plus c on the inside moves it to the left, and minus c on the inside moves to the right. This negative out front reflects it across the x-axis, the negative inside across the y-axis. C times b to the power of x stretches it vertically. And then if it's that value is between 0 and 1, it shrinks vertically. And then some constant on the x and the exponent horizontally stretches and shrinks our graph. Now, probably the shifts we see the most are the shifting up, down, left, and right, and maybe a vertical stretch or shrink, or flipping across the x-axis, but we usually don't do too much of the horizontal stretch and then shrink. So here it asks us to graph and to state our domain and range. I'm going to write D and R just as a reminder to myself that I need to state the domain and range. And so looking at my function here, I have 1/3 to the power of x. I'm not going to use as many points as I used in those first couple examples. Right now, I'm going to use 5 points, but as we do more examples, I'm going to get down to 3. And typically when you graph exponential functions, 3 will be enough. Right now, I'm going to use -2, -1, 0, 1, and 2. I'll probably only do this example with 5 points. So 1/3 to the -2 power, that negative will flip it, and then squared would be 9. 1/3 to the -1 will be 3. 1/3 to the 0 power is just 1. 1/3 to the first power is 1/3, and 1/3 squared is 1/9. And hopefully you're noticing this kind of reciprocal pattern here with these values. That'll continue to be the case. So at -2, we got 9. So 1, 2, 3, 4, 5, 6, 7, 8, 9. And -1, we got 3, 1, 1/3, and 1/9. And we can see this decay function. And we want to include that horizontal asymptote with our graph. So I should see that asymptote graph for all exponential functions. Now, we haven't talked about the domain and range of these functions yet, so let's talk about that really briefly. The domain is going to be always all real numbers, so -infinity to +infinity for exponential functions. There's no restrictions on what I can plug in. I can plug in as far negative or as far positive as I want. But for the range, those y values, notice that I haven't even graphed anything down here. I made my x-axis super low because I have nothing going on down here. There's no x value or no function values below the x-axis. And so my range goes from 0 to infinity. Now it never actually touches 0. So my range is a parenthesis on 0 to infinity, not a bracket because it does not equal 0. Okay, so that's the domain and range for that function. Let's do a few more graphs here. And I have 3/2 to the power of x. And now I'm going to go to just using 3 points. I'm going to use -1, 0, and 1. And when I plug in -1, 3/2 to the -1 power, that's 3 to the -1 and 2 to the -1, and those move. So that becomes 2/3. Anything to the 0 power is 1, and 3/2 to the first power is 3/2. So I can go ahead and plot those values now. And 2/3 is a little less than 1, and then a 1, and then a little more than 1. So this is a very slow growth function. And oops, I messed my graph up there a little bit. That's okay. And we have a horizontal asymptote at the x-axis still. And then my domain, again, is going to be -infinity to +infinity. And my range, again, 0 and goes up to infinity. When we start seeing some shifts, we will see our domain and range change. But at this point, we haven't started using any shifts yet. So here we have the natural function or the natural exponential function. And we have e to the power of 2x. Remember, e is approximately 2.71. So making a table, I'm going to use those same x values, -1, 0, and 1. And then I have h of x that I'm graphing. If I plug in -1, I have e to the -2 power. If you were to type that into your calculator, you're going to get a pretty small decimal here. And you're going to end up with about 0.14. If you plug in 0, 0 times 2 is 0. E to the 0 is just 1. And then if you plug in 1, 1 times 2 is 2. So e squared, which if you type that in your calculator, you get approximately 7.3. So we have some values that we can go ahead and plot. And I have at -1, a really tiny decimal. At 0, I have 1. And then at 1, I have 1, 2, 3, 4, 5, 6, 7.3, so a little above 7. So we have a very, very steep growth function here. But again, it's getting really close to the x-axis, but it will never actually touch it. So we have that horizontal axis there. And again, our domain and range, our domain is -infinity to +infinity, and our range goes from 0 to infinity. All right, now in these next two examples, we see some shifts showing up. And so we have these shifts here, 1/4 to the power of x, And then we've got that -2. So that -2 is shifting our graph down 2. Now, when I make my table, I'm going to still use -1, 0, and 1. But I'm just going to do 1/4 to the power of x without the shift. So 1/4 to the power of x, or to the power of -1 is 4. 1/4 to the 0 power is 1. And 1/4 to the first power is 1/4. So I can go ahead and plot those points. Even though that's not the graph that I'm actually interested in, I'm going to start with those points. So -1, 4, 0, 1, and 1, 1, 4. And then they're all going to shift down 2. But in addition to those shifting down 2, my asymptote is normally the x-axis. It will also shift down 2. So now we'll be here at y equals -2. So all of these points are moving down 2. And that is the graph that I'm actually interested in graphing. So my domain and a range for that graph, my domain is still -infinity to +infinity, but my range now goes from -2 to infinity, still a parenthesis on the -2, because it doesn't actually equal -2. It doesn't touch -2, but it gets really, really close to it. All right, one more example, and then I think we'll end this video there and kind of cut this section in half. Here I have 4 to the power of x plus 1 and then -2. That +1 in the exponent shifts my graph to the left 1. And then the -2 is down 2. All right, so I'm going to go ahead and make a table real quick. X, and I'm going to do 4 to the power of x, -1, 0, and 1. 4 to the -1 is 1/4. 4 to the 0 is 1. 4 to the first power is 4. And I'm going to plot those points. So I have -1, 1/4, 0, 1, and 1, 4. And all of these points are moving left 1 and down 2. So left 1 and down 2. Left 1 and down 2. Left 1 and down 2. And that means my my horizontal asymptote also got shifted down 2. Shifting right and left doesn't affect my horizontal asymptote. Only shifting up and down does. So this shifted graph here is k of x. And that's the shifted graph there. All right. And then the domain and the range, -infinity to +infinity, and my range is -2 to infinity. And that is the end of this section.